picture, for a moment, a small world drifting far from the warm light of the sun. Its surface is white and pale, cracked like an old porcelain bowl, glittering faintly under starlight. The temperature there is so cold that nothing on earth could survive a single breath of it. And yet, somewhere beneath that frozen crust, miles below the silent ice, a vast dark ocean may be slowly turning salt water, liquid, possibly older than our entire planet. This is the quiet wonder we will sit with tonight. Across our solar system, scientists have found gentle hints, strange clues, and soft whispers in the data, all pointing to the same astonishing idea. Hidden inside small moons and distant dwarf planets, sealed away under shells of ice, there may be more liquid water than exists in all the seas of Earth combined. Not on the surface, not warmed by any sun, but buried, sheltered, patient. Imagine looking down from far above one of these worlds. You see no blue, no clouds, no coastlines, only a dim, pale globe, scratched with long curving lines like cracks in winter glass. The surface might be older than the dinosaurs by a wide margin, frozen so hard it behaves more like rock than ice. From orbit, the world looks dead, silent, forgotten, and that, perhaps, is the deepest part of the mystery. The signs of an ocean are almost never visible from above. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. To picture what may lie beneath, slow your mind and travel downward, past the surface ice, which can be many miles thick, past layers of older, slower ice that creeps like cold honey across billions of years, past faint cracks where warmer material may rise. And then, somewhere in that great quiet darkness, the ice gives way. Below it stretches an ocean, lightless, cold, near the top, possibly warmer near the rocky floor, salty in ways we are still trying to measure, and nobody in all of human history has ever seen it directly. Several moons in our own neighborhood may hold such oceans. Europa, the smooth white moon of Jupiter, whose cracked face hints at a sea beneath. Enceladus, a tiny moon of Saturn, which sprays plumes of water into space from fractures near its south pole. Ganymede, the largest moon in the solar system, which carries a magnetic whisper suggesting deep salty water far below. Callisto, Titan, possibly even Pluto, each one different, each one shy, each one hiding something we can only guess at. The question that pulls us forward through these long hours is simple to ask and very hard to answer. If our own quiet corner of the galaxy holds this many hidden oceans, what does that mean for the rest of the universe? Some researchers wonder whether ocean worlds might be the most common kind of habitable place in existence, far more common than sunlit planets like our own. Others are more cautious. They point out that we have never directly sampled one of these oceans, and that habitable and inhabited are very different words. That tension is where we will rest tonight. We will not solve it. Nobody can, not yet. The drills, the probes, the listening instruments that might one day reach through these icy shells have not been built, or are only beginning to be designed. For now, we listen to faint magnetic signals. We study the chemistry of tiny ice grains caught from a passing plume. We measure how a moon wobbles as it orbits, and try to guess from that wobble whether something liquid sloshes inside. These are gentle clues, beautiful, but incomplete. A theory built on them is a theory built on whispers. So this is what we will do together. We will travel slowly from world to world. We will look at the cracked white face of Europa, the soft icy spray of Enceladus, the strange buried sea below Titan's orange haze, the deep silent waters that may rest inside Ganymede and Callisto, and even Pluto. We will sit with the question of how an ocean stays liquid in such terrible cold. We will wonder, quietly, whether anything moves down there, anything at all. You do not need to follow every detail. You do not need to remember anything. Let the words drift over you the way starlight drifts across an icy plain. The mystery is patient. It has waited billions of years already. It can wait a little longer while you rest. Let us begin with something simple. A hidden ocean, in the way we mean it tonight, is a layer of liquid water tucked between a thick crust of ice on the outside and a core of rock on the inside. Picture a frozen pond on a winter night. Beneath the white skin of ice, the water is still there, still moving, still dark and cold and alive with quiet motion. Now imagine that pond wrapped completely around a small world, going all the way around, like the skin on a piece of fruit. That is the shape we are talking about. These oceans sit on moons and dwarf planets that orbit far from the sun. Out there, sunlight is faint. On Europa, a moon of Jupiter, the sun in the sky is about 25 times dimmer than it is here. On Enceladus, a moon of Saturn, the sun is 100 times fainter. Surface temperatures fall to something close to minus 160 degrees Celsius, cold enough to freeze the breath out of any living thing in an instant. And yet, somewhere below that frozen skin, the water stays liquid. That is the puzzle. That is what scientists have been turning over in their minds for the last few decades. The first soft hints came in the 1970s, when the Voyager spacecraft flew past the outer planets and sent back pictures of their moons. Europa looked strange. Its surface was smooth, almost too smooth, crossed by long brown cracks, like the seams on a cracked egg. There were almost no craters, which was puzzling, because every old surface in the outer solar system is pocked with craters. Something had to be erasing them. Something underneath, perhaps, was pushing up fresh ice and smoothing the face of the moon over and over again across the ages. Then came the Galileo mission in the 1990s, which spent years orbiting Jupiter and studying its moons up close. Galileo carried a small instrument that measured magnetic fields. When it passed close to Europa, it sensed a faint magnetic signal that seemed to wobble in time with Jupiter's own powerful magnetism. The simplest way to explain that wobble was to imagine a layer of salty, electrically conducting fluid inside the moon. Salty water fits that description very well. The same kind of measurement, taken at Ganymede and Callisto, suggested those moons might be hiding oceans too. Now, none of this is direct proof. No one has ever seen one of these oceans with their own eyes. No probe has ever touched the water. The evidence is all gathered from the outside, from gravity readings and magnetic measurements, and the shapes of cracks in the ice. Some researchers point out that other explanations are still possible. A layer of warm, soft ice, for example, might mimic some of these signals without being fully liquid. The case is strong, but it is not closed. Let us put some numbers on these worlds, gently, just to give them shape in your mind. Europa is about the size of our own moon, a little smaller, roughly 3,100 kilometers across. Its ice shell may be somewhere between 15 and 25 kilometers thick, though no one knows for sure. Beneath that, the ocean could be 100 kilometers deep. If those numbers are right, Europa holds more than twice as much liquid water as all the oceans of Earth combined. A moon smaller than ours, carrying twice our seas inside it. Enceladus is much tinier, only about 500 kilometers across. You could fit it inside the state of Arizona. And yet this small world appears to have a global ocean too, just under its southern ice. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. Its hidden ocean may sit sandwiched between layers of different kinds of ice, the way the filling sits between two slices of bread. These worlds are old. The solar system itself is about 4.5 billion years old, and these moons formed not long after. If their oceans have been liquid for most of that time, then we are talking about bodies of water that have been quietly sloshing in the dark for longer than life has existed on Earth. That, perhaps, is the part that most invites wondering. Time. Enough for almost anything. Time enough for chemistry to do slow, patient work in the lightless coal. How much of this picture is correct, and how much will be rewritten by the next generation of spacecraft? No one yet knows. The basics, as we now hold them, are these: many worlds, thick ice, possible oceans, and a long, long stretch of time in which something or nothing has been happening below. To understand how an ocean can hide beneath a shell of ice, we have to travel back in time, back to the long, slow birth of the outer solar system, when the worlds we know today were only beginning to take shape. The story begins not with water, but with cold dust and gas drifting in the dark around a young sun. In those early days, a wide disk of material spun slowly around our star. Closer in, the heat was strong enough to keep most water as vapor. Farther out, past a quiet boundary scientists call the frost line, the temperature dropped low enough for water to freeze. There, tiny ice grains began to stick together, joining with bits of rock and dust. Slowly, over millions of years, those grains gathered into pebbles, then boulders, then small worlds. The giant planets formed first, pulling in huge amounts of gas and ice. Around each of them, a smaller disk of leftover material began to spin. From those smaller disks, moons were born, and because they formed past the frost line, many of them began their lives already rich in water ice. Some may have been nearly half ice by mass when they finished forming. At first, these young moons were warm. The heat came from the energy of their formation, from the constant impacts of incoming debris, and from the slow decay of radioactive elements buried inside their rocky cores. Under that early warmth, the ice melted from within. Heavier rock sank toward the center. Lighter water rose toward the surface. In this way, many of these worlds may have separated into layers, like a slow, cold cousin of how Earth sorted itself into core, mantle, and crust. What happened next is where the mystery deepens. The outer shells of these moons faced the brutal cold of deep space, where temperatures can fall below -180 degrees Celsius. The surface water froze quickly into a hard crust, but beneath that crust, the situation was different. Pressure rose with depth. Heat from the core kept seeping outward, and in many cases, the liquid layer became trapped, sealed in by its own frozen ceiling above, and a warm floor of rock below. That is one part of the story most researchers agree on, but the next part is far less settled. For an ocean to remain liquid for billions of years, something has to keep adding heat. The original warmth from formation would have faded long ago. Radioactive decay alone may not be enough, especially in smaller moons. So how do these hidden seas survive? One leading idea points to tidal flexing. As a moon orbits a giant planet, the planet's gravity pulls harder on the near side than the far side. The moon gets gently stretched and squeezed, over and over, as it travels its orbit. That constant flexing creates friction deep inside, and friction creates heat. Some researchers think this slow squeezing is the main reason oceans on places like Europa and Enceladus have lasted so long. Competing view suggests that tidal heating alone cannot explain every case. Worlds, like Callisto, which sits farther from its giant planet and feels less of that gravitational tug, may still hold a liquid layer. If that proves true, then something else must be at work. Perhaps thick layers of salts and ammonia act like a kind of natural antifreeze, keeping water liquid at temperatures that would otherwise freeze it solid. Perhaps the rocky cores of these moons hold more heat than we thought. The evidence is still incomplete. There is also a quieter question hidden inside all of this. We do not fully know how thick the ice shells really are. On some moons, the shell may be only a few kilometers deep. On others, it may stretch 100 kilometers or more before reaching liquid. The thickness shapes everything: how much heat escapes, how the ocean churns, whether any of its water ever reaches the surface. And every moon seems to tell a slightly different story. So when you picture one of these hidden oceans, picture a long, slow birth, a young moon, rich in ice, forming in the cold outer reaches of a newborn solar system. A surface that froze fast and hard, a deep interior that stayed warm, perhaps from the gentle pull of a giant planet, perhaps from chemistry we have not fully mapped, perhaps from a quiet mix of both. Picture the ice and the water settling into their long, patient arrangement, sealed away from the stars above. How exactly each of these oceans came to be, and what keeps each one liquid today, remains one of the gentler mysteries of planetary science. The shells are real. The seas seem real. The full origin story, for now, is still being written. To understand how an ocean can stay liquid inside a moon that sits hundreds of millions of miles from the sun, we have to think about a very strange kind of warmth. It is not the warmth of sunlight. It is not even the warmth of a hot core left over from a planet's birth. It is the warmth of squeezing, the warmth of being pulled and pressed by gravity over and over for billions of years. Picture a small, icy moon orbiting a giant planet. The giant pulls on the moon with enormous force. The near side of the moon feels a slightly stronger tug than the far side. This tiny difference stretches the moon just a little into the shape of an egg. As the moon travels around its parent world, that stretching shifts. The bulge moves, the rock and ice inside flex, and flexing, like bending a paperclip back and forth, creates heat. This process is called tidal heating. It is one of the quiet engines of the outer solar system. Without it, moons like Europa and Enceladus would likely be frozen solid all the way through. With it, they may hold seas larger than any on Earth. The materials that make up these worlds matter just as much as the squeezing. Most ocean moons are built from a mix of rock, metal, and water ice. The rocky cores hold silicates, minerals rich in silicon and oxygen, the same family of minerals that form the crust beneath your feet. The metals are mostly iron and nickel, the heavy elements forged long ago in the hearts of dying stars. Every atom of iron in an icy moon's core was once cooked inside a sun that lived and died before our own sun was born. That iron drifted through the dark for ages, gathered into clouds, and eventually settled into the small worlds we now study. Wrapped around these cores are shells of water ice, sometimes mixed with ammonia, methane, or salts. The water itself is an ancient traveler. Some of it may have formed in cold molecular clouds before the solar system existed. Some may have ridden in on comets and small icy bodies during the chaotic early days of planet building. The water in Europa's hidden sea, if it exists as scientists suspect, may be older than the sun by a wide margin. That same water might be chemically related to the water in your glass tonight. The way these materials respond to squeezing is what allows oceans to survive. Ice, under pressure, behaves in unusual ways. Push it hard enough, and it begins to flow. Slowly, like very thick honey, add a little ammonia or salt, and the freezing point drops, letting water stay liquid at temperatures far below zero. Researchers think the oceans inside these moons may be briny, perhaps as salty as Earth's seas, perhaps far saltier. Some may be slightly alkaline, others may be more acidic. We do not yet know for sure. There is also the question of how much heat tidal squeezing actually produces. One view holds that the flexing is enough on its own to keep large oceans liquid for billions of years. Another view suggests that radioactive elements in the rocky core, uranium, thorium, potassium, provide a steady second source of warmth, slowly decaying and releasing energy into the surrounding ice and water. Most likely both processes work together in proportions that differ from moon to moon. Which one dominates in any given world is still an open question. The chemistry at the bottom of these oceans may be the most interesting part. Where warm rock meets cold water, minerals dissolve. Hydrogen, carbon, sulfur, and other elements seep into the sea. On Earth, this kind of meeting point creates hydrothermal vents where strange ecosystems thrive without sunlight. Whether the same kind of chemistry is happening inside Europa or Enceladus right now is something we genuinely do not know. The ingredients seem to be there. The energy may be there. What is happening in the dark is still hidden from us. Every part of these worlds is borrowed from somewhere older. The iron from dead stars, the water from interstellar clouds, the salts from rocks that formed in the early solar nebula, the heat from gravity itself, pulling endlessly across empty space. When you imagine an ocean inside a moon, you are imagining a place where ancient matter, ancient water, and a strange slow warmth have come together in conditions we still barely understand. The recipe is shared across the galaxy. The outcome, in any given world, remains a mystery we are only beginning to read. Of all the icy moons we know, none has caught the imagination quite like Europa. It is the smallest of Jupiter's 4 large moons, only a little smaller than our own moon, and from a distance it looks almost gentle, a soft pale sphere, the color of old bone, glowing in reflected sunlight. The surface is bright because it is mostly water ice, fresh and clean and reflective. Yet, when you draw closer, the gentleness gives way to something stranger. The whole face of Europa is laced with long, dark cracks, running in every direction, crossing one another in patterns that look almost drawn by hand. These cracks are the clue. They are the visible record of forces working in silence, deep below, over enormous spans of time. To understand why Europa is cracked, you have to understand where it sits. Jupiter is a giant. Its gravity is the strongest in the solar system after the Sun, and Europa orbits it closely, looping around once every 3.5 Earth days. That close, that fast, gravity is not a gentle pull. It is a constant tug, stronger on the near side of the moon than the far side. This unequal pull stretches Europa very slightly into a faintly egg-shaped form. If Europa's orbit were a perfect circle, that stretch would stay fixed, and the moon would not feel much. But the orbit is not a perfect circle. It is just slightly oval, and that small ovalness is everything. As Europa swings closer to Jupiter, the stretch grows. As it swings farther away, the stretch eases. The whole moon flexes in and out every few days, like a slow heartbeat. The bulge rises and falls by perhaps 30 meters, give or take, depending on whose model you ask. That is taller than a 10-story building, rising and falling across the body of an entire world. This flexing is the engine of everything. When a solid body bends back and forth, it warms. You can feel this yourself by bending a paperclip rapidly until the metal becomes hot to the touch. Europa does the same thing on a planetary scale, only the bending never stops. The heat generated by this endless gravitational kneading is, most researchers think, what keeps the inner ocean from freezing solid. Without Jupiter's pull, Europa would likely be a frozen ball all the way through. With it, the depths stay liquid. The cracks on the surface are how the shell answers back. Ice is brittle when it bends too fast. As the tidal bulge rolls around Europa, with each orbit, the icy crust pulls and shifts, and it cannot quite keep up, so it breaks. Long fractures open, and then heal as fresh water or slush rises and freezes. Newer cracks cross older ones. Some run for thousands of kilometers, longer than continents on Earth. Others curve in graceful arcs that planetary scientists believe may trace where the ice shell has slowly rotated, slipping over the ocean beneath like a loose skin. The colors hint at chemistry. Most of Europa is white or pale gray, but the cracks are stained reddish-brown. What that staining actually is remains an open question. One idea is that salts from the ocean below have been pushed up through the fractures and then darkened by Jupiter's harsh radiation. Another idea is that the stains are sulfur compounds, possibly delivered from the volcanoes of Io, Jupiter's neighboring moon. A third possibility is that they are organic molecules, carbon-based chemistry from the interior. We do not yet know which, or whether it is some mix of all three. There are other forces at work too. Jupiter bathes Europa in intense radiation, a steady storm of charged particles that would be lethal to a human in minutes. This radiation slowly cooks the surface ice, breaking water molecules apart and rearranging the chemistry of the top few meters. Some researchers wonder whether this surface chemistry might eventually trickle down through cracks, feeding the ocean below with fresh ingredients. Others suspect the shell is too thick and too sealed for much exchange. The truth probably lies somewhere between, but exactly where is still being debated. So Europa is shaped quietly by a balance of unseen pressures, gravity tugging unevenly, tides flexing endlessly, heat seeping from within, radiation working at the skin, salts and unknown compounds rising through fractures, only to be altered by light they were never meant to meet. The result is a world that looks still from a distance, yet is constantly moving on timescales we cannot easily watch. A pale, cracked sphere, holding its dark ocean steady against the cold by the slow, patient work of forces. Now, we turn our quiet attention to a small moon called Enceladus, and the strange icy mist it breathes into the dark. To understand what we are looking at, let us begin with its size. Enceladus is tiny. If our Earth were the size of a basketball, Enceladus would be smaller than a grape. Its whole surface is about as wide as the state of Arizona. You could drive across it in a long day if there were roads, and if there were any reason to drive across a frozen white ball at the edge of the solar system. And yet, despite being so small, this little world does something no one expected. From cracks near its south pole, it sprays great curtains of water vapor and ice grains far out into space. The plumes rise hundreds of miles above the surface. Some of the particles escape the moon entirely and feed a faint ring around Saturn. A speck of ice that flies out of Enceladus today may still be drifting through the Saturn system long after you have fallen asleep tonight. Picture the scale of this gentle fountain. Imagine a snow globe the size of a small country, and from a few thin cracks on its underside, a steady mist climbs upward, slow and silent, into a sky that has no air. The mist does not fall back the way snow falls on Earth. Some of it freezes into glittering grains and rains softly down onto the ice. Some of it drifts away forever. The cracks themselves are known as the tiger stripes. There are 4 of them, each roughly 80 miles long, cut into the ice near the South Pole. They are warmer than the rest of the moon. Not warm by our standards, of course. The surface of Enceladus sits at around -330 degrees Fahrenheit. The tiger stripes are perhaps 100 degrees warmer than that, which is still colder than anywhere on Earth has ever been. Yet, against the deep cold of the surrounding ice, those stripes glow like faint embers in an infrared view. Now consider what the plumes carry. When a spacecraft flew through them, it tasted the spray. Inside, the icy grains were salts, simple organic molecules, and tiny grains of silica. Those silica grains are especially interesting. On Earth, silica of that particular size forms when hot water, around 90 degrees Celsius, reacts with rock. That is roughly the temperature of a hot cup of tea. So somewhere beneath the ice of this little grape-sized moon, water may be touching warm rock at the bottom of a hidden sea. Let that scale settle for a moment. The ocean of Enceladus is thought to sit beneath an ice shell, perhaps a dozen miles thick, maybe more in places, maybe thinner near the South Pole. Below that shell lies a global sea, possibly around 25 miles deep. That is deeper than the deepest trench in Earth's oceans. On a moon you could nearly fit inside Texas. There may be a body of salt water more than 4 times as deep as the Mariana Trench. How can something so small hold so much warmth and so much liquid water for so long? That part of the mystery is still being argued. The leading idea is tidal flexing. Enceladus follows a slightly stretched path around Saturn, and the giant planet's gravity squeezes and releases the moon over and over. That endless squeezing turns into heat, the way a paperclip warms slightly when you bend it back and forth. Some researchers, though, wonder whether tidal flexing alone is enough. The numbers do not always add up neatly. There may be other sources of heat we have not yet identified, perhaps locked inside the rocky core, perhaps shifting with time. There is also the question of how long the plumes have been spraying. If they have been venting steadily for billions of years, the ocean has had a very long quiet time in which something interesting could happen. If they switch on and off across the ages, the picture changes. We simply do not know yet. What we do know is that we are looking at the smallest world in our solar system that openly shows us its hidden sea. The plumes are an invitation. They lift the contents of that buried ocean into space, where a passing spacecraft can sample them without ever drilling through a single inch of ice. A tiny moon, smaller than many countries on Earth, is gently handing us its secrets, one frozen droplet at a time. And still, after all our sampling, the deepest question floats unanswered in the cold dark above those 4 glowing stripes. Imagine you are drifting down through a thick golden haze, a sky the color of weak tea poured through old amber. The light is dim here, soft as candle glow seen through fog. Titan's atmosphere is denser than Earth's, and it muffles the sunlight before it ever reaches the ground. By the time you settle onto the surface, the world around you feels like a quiet dream, lit by a single distant lamp. The ground beneath your feet is not quite like anything on Earth. In some places it looks like dark sand, fine and packed and rippled into long dunes that stretch for hundreds of miles. The grains are not the silica you would find on a beach back home, They are tiny particles of frozen carbon-rich matter, perhaps something close to soot, drifted into shapes by a slow, patient wind. The dunes glow faintly orange-brown under the hazy sky, like cinnamon scattered across a tabletop. In other places, the surface turns harder, paler and more broken. Bright, icy hills rise out of the gloom, made not of rock, but of water ice frozen so cold it behaves like stone. Channels wind between them, carved by something that flowed long ago and may still flow today. There are lakes here, real lakes, glinting darkly in the dim light. But the liquid inside them is not water. It is methane and ethane, the same gases we burn for fuel on Earth, kept liquid by the deep cold. The lakes lie flat and oily and still, reflecting the orange sky like polished obsidian. You could stand at the edge of one of these lakes and hear almost nothing. Titan is cold, around minus 290 degrees Fahrenheit at the surface, but the thick air carries sound well. A breeze through the dunes might whisper in a low, slow tone. A drop of methane rain, falling from a cloud overhead, would land with a soft, heavy plop, slower than rain on Earth, because the gravity is weaker and the air is thicker. Raindrops here fall like floating feathers, taking long, lazy seconds to reach the ground. And yet, beneath all of this strange, frigid scenery, beneath the dunes and the methane lakes and the bright water ice hills, there is something even stranger. Deep below the crust, perhaps 50 miles down or more, planetary scientists believe Titan hides a vast ocean of liquid water. Not methane this time, real water, the kind you could drink if it were not pressurized and salty and sealed away under miles of ice. The evidence comes from careful study of how Titan flexes as it orbits Saturn. The moon's shape shifts slightly with the pull of its giant parent, and the way it shifts hints that something soft and liquid is sloshing inside. Gravity measurements from the Cassini spacecraft suggested the same thing. One reading of the data points to a deep, salty sea, possibly as briny as the Dead Sea on Earth, possibly even saltier. Another reading suggests the ocean might be less salty, but layered, with denser fluid sitting beneath lighter fluid. Both pictures fit the numbers we have. Neither is proven. What would this hidden ocean look like if you could somehow see it? It would be utterly black. No sunlight reaches that depth. The water would press against the underside of the ice shell with enormous force, and against the rocky core far below with even more. It might be quiet, or it might churn with slow convection currents, driven by heat from inside the moon. We simply do not know. Some researchers wonder whether the ocean connects, even in trickles, to the surface world above. If methane and complex organic compounds from the haze can sift down through cracks, and if water from below can occasionally well up, then Titan might be a place where two different chemistries meet. Others think the ice shell is too thick and too solid for any real exchange. The shell could be tens of miles deep, sealing the inner sea away from the outer skin completely. The question of how separate or how connected these two layers really are remains genuinely open. So picture it once more: the orange sky, the dark dunes, the black mirror lakes of liquid gas, the pale ice hills standing in the gloom, and far below all of that, hidden under miles of frozen crust, a salty sea you cannot see, cannot reach, cannot yet sample. A whole ocean on a moon of a ringed planet, wrapped in haze and silence. Whether anything stirs in those depths, or whether they sit forever still and dark, no one on Earth yet knows. Far from the warmth of the sun, circling the great striped planet Jupiter, there moves a world larger than the planet Mercury. Its name is Ganymede. It is the biggest moon in the entire solar system, and if it orbited the Sun on its own, we would surely call it a planet. Yet for all its size, Ganymede keeps quiet company in the shadow of its giant parent. Its surface is a strange mix of dark, ancient terrain and bright grooved patches that look almost combed by some invisible hand. And beneath that crust, the evidence suggests, lies one of the most remarkable secrets in our neighborhood of space. To understand what hides inside Ganymede, picture the moon in cross-section, as if a careful knife had sliced it in half. At the very center sits a small core of iron, still warm, still slowly stirring. Wrapped around that core is a thick mantle of rock, and above the rock, the strangest part begins. Layers of ice and water seem to stack on top of one another, alternating like the pages of a book left out in the snow. At certain depths, the pressure is so great that water freezes into forms of ice, unlike the ice in your freezer at home. These exotic ices are denser than liquid water, so they sink. Between these layers, liquid oceans may sit, trapped and dark, never seeing the surface. The first strong hint came from a spacecraft called Galileo, which flew past Ganymede in the 1990s. As it passed, its instruments noticed something curious about the moon's magnetic field. Ganymede has its own magnetic field, the only moon known to generate one. But layered on top of that was a second, weaker signal that wobbled in just the way salt water would wobble if Jupiter's powerful magnetic field were sweeping past it. Later, astronomers using a space telescope watched the glowing rings of charged particles dancing above Ganymede's poles. The way those rings rocked back and forth matched what you would expect if a deep, salty ocean were hidden under the ice, gently pushing back against Jupiter's pull. If those readings are correct, the ocean inside Ganymede may hold more water than all the seas on Earth combined. Some estimates suggest it could be 10 times deeper than our deepest trench. It would be utterly dark down there, pressed under many miles of ice, far heavier than any pressure a human submarine has ever faced. The water would be cold, salty, and still. Yet here the open questions begin. Scientists are not certain how this ocean is arranged. One picture suggests a single great sea, sandwiched between an upper ice shell and a lower layer of exotic high-pressure ice. Another picture, supported by careful computer models, suggests something stranger. The interior may be a club sandwich of alternating layers: ice, then water, then a denser ice, then more water, then yet another ice, down and down toward the rocky mantle. If that is true, Ganymede could hold not one ocean, but several, stacked like floors in a quiet, flooded building. This matters more than it might seem at first. On Europa and Enceladus, the ocean appears to sit directly against warm rock, which would allow minerals and chemistry from the seafloor to mix into the water. On Ganymede, if exotic ice separates the deepest ocean from the rock below, that mixing might never happen. Some researchers wonder whether life, if it could begin anywhere, would struggle in a sea cut off from stone. Others suggest that even thin contacts, or slow seeping over billions of years, might be enough to season the water with the chemistry life needs. The argument is far from settled. The heat that keeps any of this liquid is another puzzle. Ganymede does feel tidal squeezing from Jupiter, but less than Europa does. Some of its inner warmth may simply be leftover heat from its formation, slowly leaking outward through the ages. Whether that warmth is enough to keep the whole sandwich liquid for the entire history of the solar system, no one fully knows. A spacecraft called JUICE is now traveling toward the Jupiter system, with Ganymede as a main target. In the years ahead, it will settle into orbit around this giant moon and listen carefully, measuring the gravity and the magnetic whispers in far more detail than ever before. It may tell us how thick the ice is. It may tell us how deep the water runs. It may even hint at what flavor of salt is dissolved in those silent depths. Until then, the largest moon in the solar system keeps its quiet secret beneath miles of pale grooved ice, waiting. Of all the icy moons in our solar system, Callisto may be the strangest puzzle. It is the outermost of Jupiter's 4 large moons, and from a distance it looks half asleep. Its surface is the most heavily cratered of any world we know. Every dent and pockmark seems to have been preserved, like footprints in old snow that no wind ever came to brush away. Nothing has resurfaced it. No fresh ice has welled up, no cracks like Europa's run across its face. And yet, deep inside this quiet ancient body, there may be an ocean. That possibility is what makes Callisto such a soft, unresolved mystery. The other ocean moons have rhythms we can almost feel. Europa flexes in time with Jupiter's pull. Enceladus puffs out water like slow breathing. Io glows with restless heat, but Callisto orbits farther out, in a wider, slower lane. Does not share a tight, gravitational dance with the other big moons. There is no strong tidal squeezing to keep its insides warm. By every simple rule we know, Callisto should be frozen solid all the way through. The hint that it is not came from a magnetic whisper. When the Galileo spacecraft passed by Callisto in the late 1990s, it noticed something gentle and strange. Jupiter's own powerful magnetic field sweeps past its moons as the giant planet rotates. When that field washes over a moon with a salty liquid layer inside, the salt water acts like a soft mirror. It pushes back with a small magnetic response of its own. Galileo measured exactly that kind of response at Callisto. The simplest reading was that somewhere beneath the dark, dusty crust, a layer of briny water lay hidden. But the reading is not airtight. Some researchers wonder whether the signal could come from something other than an ocean. A layer of partially melted ice, mixed with minerals, might behave a little like salt water in the right conditions, or the response might be shaped by Callisto's ionosphere, the thin shell of charged particles around it. The ocean idea fits the data well, but it is not the only door that opens. If the ocean is real, the next question is how it has lasted. On worlds like Europa, tidal flexing pours heat in steadily, like a hand rubbing cold metal until it warms. Callisto has very little of that. It sits in a calmer orbit, gently nudged, but not needed. The leading guess is that the warmth comes from within, from the slow decay of radioactive elements buried in Callisto's rocky core. That kind of heat is faint and quiet, but it is patient, spread across billions of years. It could be just enough to keep a thin layer of water from freezing, especially if that water is loaded with salts or ammonia, which lower the freezing point. This is the cycle Callisto seems to live by, if it lives by any cycle at all. Not a quick pulse of tides, not a hot, churning interior, just a deep, slow rhythm of heat trickling outward, through stone and ice, balanced against the steady cold of space. If the balance holds, the ocean stays. If it tips even slightly, the water freezes, age by age, into another layer of the shell. Picture the scene for a moment. A round, grey-brown world, its surface dusted with dark grit and pale ice. Craters of every size, layered over one another like soft echoes. No glow, no plumes, no fresh fractures. Below that quiet crust, a deep blanket of ice, perhaps 100 kilometers thick or more, and then maybe a still, dark sea. No tides crashing, no currents racing, just slow, patient water, pressed between ice above and warm rock below, turning over so gradually that a single circuit might take thousands of years. We do not know if that sea is truly there. We do not know how thick it is, or how salty, or whether it touches rock at the bottom in a way that could feed chemistry into the water. Those last details matter a great deal, because rock-water contact is one of the things scientists watch for when they wonder about life. On Europa and Enceladus, the case for such contact is stronger. On Callisto, the ocean, if it exists, may be sealed between layers of ice on both sides, locked away from the minerals it would need for any rich chemistry. So Callisto rests in our list of ocean candidates as a soft maybe, less dramatic than its siblings, slower, quieter, a world whose cycle, if it has one, beats so faintly that we can barely hear it across the dark. Far out at the edge of the planets, where the sun is no brighter than a sharp, distant star, a small world drifts in slow silence. Pluto is so far away that sunlight takes more than 5 hours to reach it. For most of human history, we knew almost nothing about its surface. It was a faint dot, a smudge in a telescope, a name on a chart. Then, in the summer of 2015, a small spacecraft slipped past it and sent back pictures that changed how we think about the cold edge of our solar system. What we saw was not a dead frozen rock. We saw mountains made of water ice, rising tall and sharp. We saw smooth plains of nitrogen ice that flowed and churned like slow taffy, and we saw a vast pale shape across one side of the world, shaped almost like a heart. The western lobe of that heart is a wide basin called Sputnik Planitia. It sits low and smooth, filled with frozen nitrogen, and it has almost no craters on its surface. That means it is young. Something keeps refreshing it. Something inside Pluto is still alive in a quiet, slow way. This is where the mystery begins. To make that flat, young surface, Pluto needs heat from somewhere. And to support certain features in its crust, some scientists believe there may be a layer of liquid water tucked deep beneath the ice. Not a warm tropical sea. Something colder, slushier, mixed with salts and ammonia that lower its freezing point. A buried, slow ocean, hidden under more than 100 miles of ice and rock. The case for this hidden sea rests on a few strange clues. Sputnik Planitia sits almost exactly opposite the side of Pluto that faces its large moon Charon. That alignment is hard to explain by chance. One idea is that the basin holds something heavy underneath, dense enough to tug Pluto into this balanced position. A pocket of liquid water, denser than the ice around it, would do the job nicely. Another clue is the lack of obvious shrinkage cracks across the surface. If Pluto's interior had frozen solid over billions of years, the world would have contracted, and we should see the scars. Instead, the surface shows signs of slow expansion, which is what you might expect if a deep ocean is only partly frozen, still giving off a trickle of heat. Yet none of this is settled. Pluto has no giant parent planet flexing it, the way Jupiter squeezes Europa. It is small, far from the sun, and should have lost its inner warmth long ago. So how could a liquid layer survive for billions of years in such a cold, quiet place? One theory points to radioactive elements deep inside Pluto's rocky core, slowly decaying and releasing heat at a low, steady rate. That gentle warmth, trapped under a thick blanket of ice, might be just enough to keep a salty slush from freezing solid. A competing view suggests the ocean, if it ever existed, has been freezing for a very long time, and what remains today may be only a thin and shrinking layer, almost gone. There is even a deeper puzzle. Some researchers wonder whether Pluto's ocean formed warm. In one picture, A young Pluto held a real liquid sea soon after it came together, and that sea has been slowly turning to ice ever since. In another picture, Pluto was always cold, and the ocean grew later as heat built up under an insulating crust. These two stories lead to very different worlds. One is an aging ocean cooling towards stillness. The other is a younger ocean still finding its shape. We do not yet know which, if either, is closer to the truth. What makes Pluto so striking is what it suggests about its neighbors. Out in the Kuiper Belt, the broad ring of icy bodies beyond Neptune, there are thousands of worlds in this same size range. Eris, Makemake, Haumea, Sedna, and many more. If little Pluto can hold a slushy sea, then perhaps some of those siblings can too. The far reaches of our solar system might be quietly dotted with buried oceans, each one sealed under miles of crust, each one waiting in the dark. We will not know for a long time. No spacecraft is on its way back to Pluto. The data we have comes from a single brief flyby, a few hours of close looking after a journey of nearly 10 years. From that small window, an enormous question has opened. A frozen heart on a tiny world may hold liquid water, or it may not. For now, the slushy interior of Pluto stays a quiet maybe, drifting at the edge of what we can see. Far out in the cold edge of our solar system, a strange moon circles the blue planet Neptune. Its name is Triton, and of all the moons we have ever found, Triton is one of the most puzzling. It moves the wrong way, while Neptune spins in one direction. Triton orbits in the other. No other large moon in our solar system does this. This single odd fact has shaped almost everything we wonder about Triton, including the chance that a hidden ocean might still slosh beneath its frozen skin. The leading idea is that Triton did not form near Neptune at all. Instead, some researchers think it began life out in the Kuiper Belt, that distant ring of icy worlds beyond the planets. Long ago, Neptune may have captured Triton with its gravity, pulling the wanderer into a tight, backwards orbit. If that is true, Triton is a cousin of Pluto that got snatched away from its family. Another view suggests a more complex capture, perhaps involving a collision or a lost partner moon. The full story is still uncertain. What we do know is that capture would have been violent. Triton's new orbit would have been long and stretched at first, and tides from Neptune would have squeezed and pulled the moon for hundreds of millions of years. That squeezing means heat, deep heat. Enough heat, perhaps, to melt the inside of Triton entirely and leave behind a global ocean of liquid water beneath an icy crust. Some models suggest that ocean could still be there today, kept warm by slow tidal flexing and by the steady decay of natural radioactive elements in Triton's rocky core. The surface we have seen supports that picture, at least a little. In 1989, a single spacecraft flew past Triton and sent back a few hours of images. What it found astonished the planetary scientists watching from Earth. Triton's surface is one of the coldest places ever measured in the solar system, about minus 235 degrees Celsius. That is colder than the surface of Pluto. Yet on this nearly frozen world, dark plumes were rising into the thin nitrogen sky. Streaks of darker material stretched downwind across the pale ground. Something inside Triton was still active. What drives those plumes remains an open question. One idea is that sunlight warms a thin layer of nitrogen ice from below, building pressure until the gas blasts upward like a geyser. Another idea is that deeper heat, maybe even from the ocean itself, pushes warm material toward the surface. The two views do not fully agree, and the data we have is decades old. Until a new mission visits, the cause of those dark plumes will stay a mystery. Triton also wears a strange face. Much of it is covered in a pattern sometimes called cantaloupe terrain. Picture the rough pitted skin of a melon, scaled up to the size of a moon. Nowhere else in the solar system shows quite this texture. Some researchers think it forms when material from below slowly rises and sinks, churning the crust in a soft, slow boil. Others wonder if it is the scar of ancient impacts reworked over time. The honest answer is that we do not know. If Triton truly does hide an ocean, that ocean would be one of the most extreme in our catalogue. It would sit beneath a shell of nitrogen and water ice, in a place where sunlight is 1,400 times weaker than at Earth. It would be cut off from the surface by miles of frozen rock-hard ice, and it would survive, if it survives at all, on the gentle warmth of tides and the slow heat of stone. There is a sadder possibility too. Some calculations suggest Triton's orbit is slowly shrinking. Tides from Neptune are pulling the moon inward, very slowly, across billions of years. Eventually Triton may pass too close to Neptune and be torn apart, forming a ring of ice and dust. Whether that happens in 3 billion years or 10 billion years depends on numbers we cannot yet pin down. For now, Triton glides on its backwards path, quiet and pink and very far from the sun. So we are left with a captured stranger, possibly hiding a sea, possibly venting from its depth, slowly spiraling toward a future end. We have seen it once, briefly, more than 30 years ago. Almost every question we asked then is still open now. Whether Triton's ocean is real, whether anything stirs within it, whether the moon itself is a borrowed visitor, or something stranger still. The little blue world keeps its secrets, turning the wrong way under a distant sun. Of all the small surprises in our solar system, few have puzzled planetary scientists quite like the little moon called Mimas. It is one of Saturn's inner moons, and at first glance it seems almost too plain to mention. It is small, only about 400 kilometers across. Its surface is heavily cratered, pale, and quiet. One enormous crater on its face gives it an oddly familiar look, almost like a single great eye staring back from the dark. For decades, scientists assumed Mimas was a frozen lump through and through, a simple ball of ice and rock, long dead inside, with no warmth left to stir. That assumption began to crack in recent years. Researchers studying old data from the Cassini spacecraft noticed something strange in the way Mimas wobbles as it orbits Saturn. The wobble is small, tiny really, but it is larger than a fully solid moon should produce. A solid frozen interior should turn smoothly, like a stone on a string. Mimas does not. It sways just a little more than expected, as if something inside it is sloshing. One leading idea is that Mimas hides a liquid water ocean beneath its icy shell. If this is true, the ocean would lie deep down, perhaps 20 to 30 kilometers below the surface. The shell above it would be thick, smooth, and ancient. The ocean itself would be young in cosmic terms, maybe only a few million to a few tens of millions of years old. That is a blink compared to the age of the moon. It would mean Mimas only recently became an ocean world, and may still be settling into that new state. Other researchers are not yet convinced. They suggest the wobble could come from a strangely shaped rocky core inside the moon. An elongated core, slightly stretched, might explain the same motion without any liquid at all. There is also the question of why the surface looks so undisturbed. On other ocean moons, we see cracks, ridges, and signs of flexing ice. Mimas shows almost none of that. Its old craters sit calm and undisturbed, as if nothing beneath them has shifted in a very long time. If a hidden sea is truly there, it has left no obvious mark above. This is part of what makes Mimas so quietly fascinating. The mystery hides in numbers, not in scenery. You cannot look at the moon and see the ocean. You can only infer it from the soft, almost imperceptible way the little world rocks back and forth as it travels around Saturn. The clue is so small that it took years of careful measurement to even notice. And once noticed, it opened a whole new question about how many other plain-looking worlds might be hiding seas of their own. There is something beautiful in the thought. For so long, scientists looked for ocean moons in places that seemed dramatic. Moons with cracked faces. Moons with stripes of warm ice. Mimas has none of those signs. It looks dull and dead. And yet the math hints that under its quiet old crust there could be a young hidden sea, dark and still and pressed against rock. If that is true, then perhaps the most boring-looking worlds deserve a second glance. Perhaps the universe keeps many of its waters in places we have not thought to check. The surface itself, viewed from far above, has a pale grey sheen, dusted with the powder of ancient impacts. The huge crater near one side is named Herschel, after the astronomer who discovered the moon long ago. Its central peak rises like a small mountain in the middle of a wide bowl. Around it, smaller craters scatter in soft chains. There are no plumes, no fractures glowing with fresh ice, just stillness, just the slow turn of a tiny world around a giant ringed planet. And below that stillness, perhaps, a hidden ocean rests, or perhaps it does not. The question is genuinely open. To settle it, we would need a future spacecraft to visit Mimas again, listening more closely, measuring more precisely, watching the wobble with patient eyes. Until then, we are left with a soft mystery, a small moon with a small motion, and a possible sea no one has seen. It is the kind of detail that planetary scientists tend to love. Not a grand discovery announced with fanfare, but a quiet shift in understanding. A reminder that even the worlds we thought we knew may still be keeping secrets. And, in the gentle wobble of Mimas, in a signal so faint it was almost missed, the solar system seems to whisper that there is still much we have not seen. Far from the warm glow of the sun, out where Uranus drifts on its tipped side, two small moons turn quietly in the dark. Their names are Ariel and Miranda. We know very little about them, and what little we know comes mostly from a single brief encounter, long ago. The story of how we learned anything at all about these worlds begins with a German-born British astronomer named William Herschel. He found Uranus itself in 1781. 6 years later, he spotted two small points of light moving with the planet. Those became Titania and Oberon, the largest of the Uranian moons. Ariel and Miranda came later. Ariel was found in 1851 by William Lassell, a brewer turned astronomer who built his own telescopes in his backyard. Miranda was not seen until 1948, when Gerard Kuiper noticed a faint smudge near the planet on a photographic plate. For decades after that, these moons were little more than dots. Telescopes from Earth could not resolve them. We knew their orbits and rough sizes, and almost nothing else. Even their surfaces were a blur. To learn more, we had to send a machine. That machine was Voyager 2. It launched in 1977, looped past Jupiter and Saturn, and then continued outward, deeper than any probe had gone before. In January of 1986, it reached Uranus. The encounter lasted only a few hours. Voyager 2 had one chance to take pictures, measure magnetic fields, and listen for clues. Then it was gone, flung onward toward Neptune. The images it sent back stunned the people waiting in mission control. Miranda, the smallest of the major moons, looked like nothing anyone had imagined. Its surface was a jumble of cliffs, grooves, and broken plates. One cliff face appeared to rise nearly 12 miles high, taller than anything known on a solid world. The terrain looked stitched together, as if pieces of different moons had been jammed into one body. Scientists called it a patchwork. They argued about how such a small world could have such a violent past. Ariel was different. Its surface showed long valleys and smooth plains that seemed to have been resurfaced at some point in the distant past. Something had erased the older craters. Something had flowed. Whether that something was water, ammonia, or a slushy mix of both, no one could say for sure. The pictures were sharp enough to raise questions, and too few to answer them. Out of those brief observations, a quiet possibility began to take shape. Perhaps these little moons had once been warmer inside. Perhaps they had even held thin layers of liquid beneath their crusts. Tidal heating from Uranus might have squeezed them long ago, just as it squeezes Europa and Enceladus today. The flexing could have melted ice deep below the surface. Then, as the orbits settled, the warmth might have faded and the oceans might have frozen, or they might not have frozen. That is the open question. Some researchers wonder whether a thin briny layer still lingers inside Ariel, kept liquid by traces of ammonia, which lowers the freezing point of water. Others argue that the moons are simply too small and too cold by now, and that any inner sea turned solid long ago. Miranda's strange cliffs hint at a turbulent past, but they do not prove anything about the present. The evidence is sparse. The case is unsettled. The frustrating truth is that we have not been back. No spacecraft has visited Uranus since Voyager 2 left in 1986. Every guess about Ariel and Miranda still rests on a few hours of data gathered nearly 40 years ago. The cameras of that era were limited. The flyby angles were imperfect. Whole hemispheres of these moons were never even photographed in good light. There are entire faces we have never truly seen. Plans for a return have been proposed many times. A mission to Uranus and its moons has appeared near the top of recent scientific wish lists. If such a mission ever launches, it would not arrive for well over a decade after leaving Earth. The patience required is enormous. The moons will still be there, of course. They have waited billions of years already. For now, Ariel and Miranda remain among the least explored worlds of any reasonable size in our solar system. They might hide remnants of ancient oceans. They might be solid through and through. The history of their discovery is really a history of brief glimpses and long silences, and the quiet possibility of buried water sits there still, waiting for someone to look again. Between Mars and Jupiter, in the cold gap where the rocky inner worlds give way to the gas giants, there drifts a wide ring of broken stone. We call it the Asteroid Belt. For a long time, most people pictured it as a dry place, a scatter of dead rocks tumbling in slow loops around the sun, scorched on one side, frozen on the other, with nothing of interest hidden inside. That picture, it turns out, may have been wrong. Drifting among those rocks is a small round world named Ceres. It is the largest object in the belt, but still tiny by planet standards. You could fit 14 Ceres inside our moon. Its surface is grey and battered, pocked with craters, dusted in clay and salt. From far away it looks like just another lump of stone. Up close, the story turns strange. When a spacecraft slipped into orbit around Ceres and began to map it carefully, the cameras caught something unexpected. bright spots, patches of pale, almost glowing material, sitting inside dark craters, so reflective they seemed to shine. At first, no one was sure what they were. Ice, perhaps, or salt, or some mix of the two, pushed up from somewhere below. The leading idea now is that those bright patches are deposits of sodium carbonate and other salts left behind when briny water seeped up through cracks and then froze or boiled away in the vacuum. That alone is a quiet shock. Salt water, recently active on a little world in the asteroid belt, not on a giant moon warmed by a giant planet. On a dwarf so small, you might think it had frozen solid billions of years ago. If the brines are real, where did they come from? The current best guess is that Ceres holds, or once held, a layer of muddy liquid beneath its outer crust. Not a clean blue ocean like Europa's, might be something thicker. A slushy, salty, ammonia-rich mixture trapped in the rock and ice, perhaps tens of kilometers down, possibly only in scattered pockets. Some researchers picture it as a global layer, very thin and very cold. Others picture isolated reservoirs, more like underground lakes than a true sea. The data does not yet pick a clear winner. There is also a softer mystery on the surface itself. Ceres has a tall, lonely mountain that looks almost like a frozen blister, rising several kilometers out of otherwise gentle terrain. One idea is that it formed as a cryovolcano, a kind of icy volcano that erupts slush instead of lava. If that is right, then Ceres has been geologically alive far more recently than anyone expected for an object its size. A competing view holds that the mountain is simply the slow ooze of an ice-rich crust, deforming over long ages without any true ocean below. Both views fit some of the evidence. Neither fits all of it. The deeper surprise is what Ceres implies about its neighbors. If a body this small, this far from any giant tidal squeeze, can hold briny water in its interior, then the asteroid belt may not be the dry rubble field we once imagined. Other large asteroids, like Pallas and Hygeia, also show hints of water-bearing minerals on their surfaces. Some appear nearly round, which suggests their interiors were once warm enough to settle into a soft shape. Whether any of them still hide damp layers inside, no one can yet say. The warming source on Ceres is itself a puzzle. There is no giant planet nearby to flex it. Tidal heating, the trick that keeps Europa and Enceladus liquid, barely applies here. Instead, the leading thought is leftover heat from radioactive elements baked into the rock when Ceres first formed, slowly trickling out over billions of years, combined with a lowered freezing point of very salty ammonia-laced water. That faint warmth might be just enough to keep a thin slush from fully solidifying. It is a delicate balance, and the models do not all agree on whether it could survive to the present day. What makes Ceres so striking is how quietly it rewrites the map. The line between dry rocks and ocean worlds was supposed to lie much further out, around the moons of Jupiter and Saturn. Ceres sits well inside that line. It suggests that liquid water, in some form, might lurk in places no one thought to look. Small worlds, lonely worlds, worlds with no glowing parent planet to warm them. If a battered dwarf in the asteroid belt can stay even slightly wet inside, the galaxy may hold many more damp hiding places than we have begun to count. The question of how common they are remains for now W. Imagine, for a moment, the boundary where an ice shell meets the sea below. It is one of the strangest places we can picture in our solar system. There is no sunlight here, no wind, only the slow press of frozen ceiling against dark water, mile upon mile thick, holding back the cold of space above. And yet this quiet boundary may be one of the most chemically active places in the galaxy. The ice itself is not pure. As an ocean slowly freezes from the top down, it tries to push out the salts and minerals dissolved in it, but it cannot push out everything. Pockets of briny liquid get trapped inside the ice. Veins of slush form. Tiny channels of salty water thread through the shell like roots through soil. Some researchers think these channels could be highways for chemistry, slowly carrying material from the surface down toward the sea, and from the sea up toward the surface. This matters because the surface and the sea need each other. On worlds like Europa, the surface is bathed in radiation from Jupiter's magnetic field. That radiation breaks apart water, ice, and creates strange molecules. Oxidants, compounds hungry to react, salts that have been chemically changed by long exposure to charged particles. If any of that material can sink through the shell and reach the ocean below, it could feed reactions that life, in theory, might use for energy. One idea is that the ice shell behaves a little like a slow conveyor belt. Warmer, softer ice rises from below. Colder, brittle ice sinks from above. Over millions of years, the surface and the deep ocean might exchange material in tiny amounts. Another view holds that the shell is mostly rigid, locked in place, and that only rare cracks or impacts allow any mixing at all. We do not yet know which picture is closer to the truth. The answer probably differs from moon to moon. The chemistry connects upward too. On Enceladus, plumes spray ocean water into space, where the sun's light slowly breaks the molecules apart. Some of that vapor falls back as a faint frost. Some escapes and joins the ring of icy dust that traces the moon's orbit. A single small world is quietly seasoning the space around Saturn with the contents of its hidden sea. The same may be happening more gently around Jupiter, where Europa's thin atmosphere carries ghosts of the ocean below. And there is the deeper link, the one that ties these moons to the giant planets they orbit. Without Jupiter, Europa would freeze solid. Without Saturn, Enceladus would go quiet. The gravity of a giant planet flexes its moons, and that flexing is the slow furnace keeping their oceans warm. The sun, so distant out here, plays almost no role. The energy source is not light, it is motion. It is the steady tug of a massive world, pulling on a small one, billions of times, year after year. This is a strange thought to hold on Earth. Almost every living thing depends in the end on sunlight. Plants drink it. Animals eat the plants. Even creatures in the deep sea rely on food that drifted down from sunlit waters far above. But in a hidden ocean beneath ice, the sun is irrelevant. The whole system runs on gravity and rock and chemistry. A different kind of engine entirely. The rock matters as much as the ice. At the bottom of these oceans, water meets the moon's stony core. Heat seeps out of that core. Slowly, water reacts with the minerals there, picking up iron, sulfur, hydrogen, and other building blocks. Some researchers suspect this rock-water boundary may be the most interesting place in the whole system, even more than the ice above. Others wonder if the cores of small moons are simply too cold and too quiet for much chemistry to happen at all. The evidence is thin in either direction, so the picture, when you stand back, is of a long, slow symphony. The giant planet pulls, the moon flexes, the core warms, the water circulates. The ice traps and releases, the radiation above bakes the surface into new compounds. The plumes vent the deep into space. Every part touches every other part, on timescales far longer than any human life. Whether any of this adds up to a place where life could begin, or where life already lives, remains one of the great open questions. We can sketch the connections, we can name the players. We cannot yet hear the full song. For now, the chemistry where ice meets sea stays mostly hidden, mixing quietly in the dark, waiting for instruments we have not yet sent. Far beneath our own oceans, where no sunlight ever reaches, there are places where the seafloor breathes, cracks open in the rock, and superheated water rises through them in dark, billowing clouds. These vents are called black smokers. They form chimneys of mineral, sometimes taller than a house, and around them gather creatures that live without sunlight at all. Tube worms wave in the current. Pale crabs walk across the warm stone. Whole ecosystems thrive in the dark, fed by chemistry instead of light. The question on the minds of many planetary scientists is simple and strange. If black smokers can power life in the deepest, darkest parts of our ocean, could similar vents be glowing softly at the bottom of those hidden alien seas? Could the floor of Europa's ocean, or Enceladus's, be dotted with warm stone chimneys, slowly building life from minerals and heat? Nobody knows, but the evidence keeps gently pointing in that direction. The clearest hint so far came from Enceladus, when the spacecraft flew through the icy plumes erupting from its south pole. It found tiny grains of silica. These grains form only when very hot water reacts with rock, at temperatures near 90 degrees Celsius. The most natural way to explain them is hydrothermal activity. Somewhere on the floor of Enceladus, hot water seems to meet cold ocean, and the chemistry of that meeting drifts upward through cracks in the ice and into space, where our instruments could taste it. That is a remarkable thing to consider while you rest. Still, the picture is not settled. Some researchers wonder if the silica grains might form by gentler processes without true vents. Maybe warm zones simmer along the seafloor without forming the towering chimneys we see on Earth. Others think the vents are real but rare, scattered widely across a dark, cold floor. The Enceladus ocean might be alive with chemistry, or it might be only quietly stirring. The grains tell us something is happening down there. They do not tell us exactly what. Europa raises the same question with even larger stakes. Its rocky core is squeezed by Jupiter's gravity, and that squeezing should release heat. One possibility is that this heat keeps the seafloor warm enough for vents to form along cracks in the rock. If so, Europa might host hydrothermal systems many times older than Earth's, working in patient silence for billions of years. A competing view is that Europa's core has cooled too much, or its rock is too smooth and unbroken, and the seafloor sits cold and still. Both ideas remain on the table. We have not yet seen the floor. What makes this so haunting is how slowly such systems would change. On Earth, a single black smoker chimney can grow over decades, then collapse, then build again. The vents shift, new cracks open, life adapts and migrates. The same patient rhythms could be playing out beneath Europa's ice right now, on timescales so long that nothing seems to move at all. A chimney might rise across 10,000 years. A colony of strange, slow creatures might cluster around it for 1,000,000 more. By the time the vent goes quiet, another could be warming the rock 100 kilometers away. There is also the question of what these vents would be made of. The minerals dissolved in an alien ocean depend on the rock below. Europa's seafloor may carry different salts and metals than Earth's. The water itself may be more acidic or stranger in chemistry than anything in our own seas. So even if vents exist, they may not look like ours. They might be paler or darker. They might build chimneys of different shapes, with different gases hissing out into the cold black water above. A more cautious view reminds us that hydrothermal activity by itself does not guarantee life. Earth has had vents for billions of years, and life here found a way to use them. Whether life on another world would do the same, we cannot say. The chemistry might simply churn without ever assembling into something that grows and copies itself. Or it might have done so long ago, in silence, with nobody watching. For tonight, picture the dark floor of an icy moon. Picture a slow drift of warm water rising from a crack in the stone, carrying minerals and faint heat upward into the lightless sea. Picture how, over centuries, that small plume might thicken, might build a soft chimney of mineral grain by mineral grain. We do not know if anything gathers there. We do not know if anything ever has. The vents may be glowing somewhere right now, patient and unwitnessed, while we rest under a kinder sky. Light has a strange relationship with these frozen worlds. On the outside, an icy shell catches whatever pale sunlight reaches it, scattering the photons back into space in soft whites and dusty creams. But beneath that shell, light cannot follow. Even a thin layer of ice, just a few meters thick, can swallow sunlight almost completely. So, when planetary scientists ask how thick the ice really is on a world like Europa or Enceladus, they are also asking how dark the ocean below truly is, and how alone any life down there might be. The thickness of these shells is one of the most quietly argued questions in planetary science. On Europa, estimates range from just a few kilometers to more than 30. That is a huge spread. The answer matters because a thin shell would mean the ocean is, in a sense, almost within reach of the surface. Cracks could open, water could rise. Sunlight, even in tiny amounts, might filter into the upper layers and feed simple chemistry. A thick shell would mean the ocean is sealed off, locked beneath kilometers of dense ice, with no light at all reaching its waters for billions of years. Two main schools of thought have grown around this question. One group of researchers favors a thin, active shell. They point to the chaotic terrain on Europa's surface, where blocks of ice look broken, rotated, and refrozen, as if warm slush once welled up from below. They look at the reddish-brown streaks along the cracks and wonder if salts and organic compounds were carried up from the ocean recently, in geological terms. In their picture, the shell breathes. It cracks, it heals. Light may even glow faintly through the thinnest patches, casting a dim blue-green hue into the upper ocean. Another group favors a thick, slow shell. They argue that the convection of ice itself, the slow churning of solid material under pressure, can explain the surface features without requiring liquid water to ever reach the top. In this view, the ice behaves a bit like a glacier on Earth, flowing imperceptibly over long stretches of time. The shell is more like a stone vault than a living skin beneath it. The ocean sits in absolute darkness, untouched by sunlight since the moon first froze over. The same debate plays out on Enceladus, though the geysers there have shifted the conversation. The plumes that shoot from the tiger stripe, fractures near the South Pole, tell us that, at least in those narrow zones, the shell is thin enough for water to find a path upward. Some models suggest the ice is only a few kilometers thick beneath those stripes, while the rest of the shell may be 20 or 30 kilometers deep. So the moon might be uneven, with most of its ocean sealed in darkness and a few cracked windows where matter, if not light, can pass. On Titan, the question grows stranger still. The ice shell there is thought to be thick, perhaps 100 kilometers, with the ocean buried far below. Above, the ice sits another world entirely, with hydrocarbon lakes that gleam dimly under the orange haze of the atmosphere. Two seas exist on the same moon, separated by a vault of frozen water, and the light that reaches one never reaches the other. What makes the thickness debate so hard to settle is that we are working from the outside. Spacecraft measure gravity, magnetic fields, and the wobble of these moons as they orbit. From those clues, scientists build models, but the models depend on assumptions about temperature, composition, and how ice behaves under enormous pressure across billions of years. Change one assumption, and the predicted thickness shifts by tens of kilometers. The data we have so far cannot pin the number down. Some researchers hope that future missions carrying ice-penetrating radar will finally give us a clear answer. Radio waves can pass through ice in ways that visible light cannot, and by listening for echoes from the boundary between ice and water, we might one day trace the underside of these shells like a sonogram. Until then, the debate continues quietly in journal pages and conference rooms. For now, the picture remains soft and uncertain. Somewhere beneath those pale white surfaces, sunlight ends. The exact depth where the last photon scatters into shadow is unknown. It might be near, it might be very far, and whatever lives or does not live in the dark waters below has never seen and may never see the star that holds its world in orbit. The thickness of the shell is, in a way, the thickness of a curtain between two utterly different worlds, and we are still trying to measure that curtain from the wrong side. Space is often called silent, and in a way it is. Sound needs something to travel through, and the vacuum between worlds carries almost nothing. Yet the worlds themselves are far from quiet. Inside the ice, beneath the ice, and within the seas below, there is motion, there is pressure, there is the slow groan of shells that flex with the pull of distant giants. We cannot stand on those moons and listen, but we have other ways of hearing. One of those ways is magnetism. It seems strange that a magnetic field could whisper the secret of an ocean, but it can. When a moon orbits a planet like Jupiter, it passes through the planet's huge magnetic field. If the moon hides a salty sea inside it, that sea acts like a faint conductor. The changing field outside induces a smaller field within the moon. Spacecraft can measure this echoed field as they fly past. The shape and timing of the echo hint at how deep the ocean lies, how salty it might be, and how thick the ice above it could be. This is how researchers first grew confident that Europa held a global sea. The Galileo spacecraft, swinging past again and again in the late 1990s, picked up a magnetic signature that flickered in step with Jupiter's rotation. The simplest explanation was a layer of conductive salt water beneath the ice. Ganymede gave a similar signal, though its own internal magnetic field made the reading harder to untangle. Callisto, quieter and stranger, hinted at the same thing. None of these readings prove an ocean beyond all doubt. Other interiors, with different minerals or partial melts, might mimic the signal. The question stays open, but the magnetic whisper is one of the strongest clues we have. Sound, in a different form, also reaches us. Spacecraft carry instruments that can capture vibrations in plasma, the thin soup of charged particles that fills space around a planet. When these vibrations are shifted into a range our ears can hear, they become eerie tones, hisses, slow whistles, low groans. Some of these recordings, taken near the gas giants, sound almost like the songs of whales heard through deep water. They are not really sound in the way we mean it on Earth. They are electromagnetic waves, translated into something a human ear can follow, but they carry information about the space around these icy worlds, about how their magnetic envelopes ripple, as charged particles stream by. Then there is the sound a moon might make to itself. Researchers wonder what it would be like to set a small instrument on the ice of Europa or Enceladus and simply listen. The shell is not still. It cracks, it shifts. Tidal forces stretch it, then let it settle. Each motion sends faint tremors through the ice. On Earth, we use such tremors, recorded by seismometers, to map the inside of our planet. The same trick might work on these moons. A wave traveling through solid ice moves differently from a wave passing through liquid water. By timing the arrivals, scientists could draw a picture of the hidden layers without ever drilling through them. No seismometer has yet listened on the surface of an ocean moon. We have only models and hopes. Some researchers think the ice would ring like a bell, with clear notes that reveal a sharp boundary between ice and water below. Others suspect the shell is too broken, too layered, too warm at the base to give clean signals. The truth may sit somewhere between, until an instrument actually rests on that frozen ground. The question of how an ocean moon truly sounds remains an exercise of imagination, guided by physics. There are also the Plumes of Enceladus, those soft fountains rising from cracks near its south pole. A spacecraft flying through them does not exactly hear them, but it does feel them. Tiny grains tap against detectors. Each tap is data. A pattern of taps, the chemistry of the particles, the way they spread into space. All of it tells a story about a sea that breathes outward through its icy lid. So, the listening goes on, indirect and patient. We read magnetic echoes. We translate plasma waves into tones. We model the seismic songs that nobody has yet recorded. From these scattered signals, a picture begins to form of seas that murmur beneath their ceilings, of ice that flexes in slow rhythms, of currents stirring in darkness we have never seen. Whether those currents carry anything alive is a separate mystery, one we will return to in time. For now, it is enough to know that even the quietest worlds may be humming softly to themselves, and we are slowly learning how to listen. To stand on the ice of Europa and drill down to the sea below, you would first have to solve a problem made entirely of numbers. The shell might be 3 kilometers thick, it might be 30. Some models stretch it past 40. Each guess changes the engineering, the power, the patience required, and the odds of ever touching the water beneath. The math begins long before any drill bit turns. It begins with orbits. To reach Europa from Earth, a spacecraft must thread a path through the inner solar system, borrow speed from Venus or Earth itself in a slow gravitational handoff, and arrive at Jupiter years later with just enough motion left to be captured. These trajectories are calculated to the second. A burn lasting a few minutes, fired at the right moment, can save years of travel. A burn fired a heartbeat late can miss the planet entirely. Once at Jupiter, the numbers grow stranger. Europa orbits its giant world in roughly 3.5 days. Io, closer in, orbits in about 1.7 days. Ganymede, farther out, takes about 7. Those 3 numbers form a quiet pattern called a Laplace resonance, where each orbit fits the next in a ratio of 1 to 2 to 4. The moons tug on each other in time with their own motion, and that gentle rhythm is what keeps their insides warm. The math of resonance is also the math of liquid water. A lander must arrive inside that rhythm. It must match velocity with a moon moving at nearly 14 kilometers per second, descend through a thin envelope of charged particles, and settle on a surface scored with ridges and cracks. The radiation environment around Europa is fierce. A spacecraft sitting on the ice would absorb in a single day what a craft near Earth might gather in a year. The electronics must be shielded, and shielding has mass, and mass costs fuel, and fuel costs more mass still. The equation folds back on itself. Then comes the drill. Researchers have sketched many designs, and the numbers behind each one are humbling. A simple heated probe, called a cryobot, might melt downward at a rate of 1 meter or 2 per day. At that pace, a 3-kilometer shell would take years to cross. A 30-kilometer shell could take a human lifetime. The probe must carry its own power source, usually a small radioactive heater, and trail a thin cable back to the surface so its findings can be sent home. The cable itself becomes a marvel of engineering, expected to survive flexing ice, shifting pressure, and temperatures near minus 170 degrees Celsius. The pressure at the base of the shell is another quiet number. On Europa, the gravity is about 1/7 of Earth's, so even a 30-kilometer column of ice presses down less heavily than you might expect. Still, the pressure at the ocean ceiling could reach tens of millions of pascals. Any vehicle entering that water must hold its shape against a force that would crumple a thin metal can in an instant. The math of materials, of wall thickness and yield strength decides what shapes are even possible. Enceladus offers a gentler set of numbers. Its shell may be only a few kilometers thick near the South Pole, and its plumes already lift ocean water into space, where a passing craft can taste it without ever landing. One theory holds that sampling those plumes is the faster path to the answer. A competing view argues that nothing beats touching the water directly, measuring its temperature, its salinity, its quiet currents. Both ideas remain on the table, and both depend on budgets and decades that have not yet been spent. There is also the matter of waiting. A mission planned today might launch in a decade, arrive in another decade, and operate for years before its first results come home. The light from Jupiter takes between 33 and 53 minutes to reach Earth, depending on where the planets sit in their orbits. Every command sent to a lander on Europa would arrive long after the moment it was needed. The craft would have to think for itself, guided by code written by people who may have retired before it ever drilled a single meter. These numbers are not obstacles so much as the shape of the problem. They describe a universe that runs on quiet, exact rules: orbital periods, melting rates, radiation doses, signal delays. Whether any of those rules will eventually allow a small machine to dip a sensor into an alien sea remains an open question. The math is patient. The ice is patient. The ocean, if it is there, has waited a very long time already, and it can wait a little longer still. If our own small family of worlds holds so many hidden seas, then the wider galaxy must be full of them. That, at least, is one quiet hope. Yet, the more we think about it, the more we notice how delicate each of these oceans really is. They survive only because a careful balance has held for a very long time, and we still do not fully understand how fragile or how stable that balance truly is. Consider what an ocean world needs. It needs water, of course, gathered long ago when the moon or planet first formed. It needs a shell of ice thick enough to seal that water in, but not so thick that the heat below cannot keep some of it melted. It needs a source of warmth, often the slow squeezing of a giant parent planet. And it needs time, billions of years of gentle, patient warmth, never quite freezing, never quite boiling away. Change any one of these, and the ocean might vanish. Move Europa a little farther from Jupiter, and the tidal squeezing weakens. The interior cools. The ocean slowly freezes from below, growing thicker year by year, until one day the sea is gone and only solid ice remains. Move it a little closer, and the heat grows fierce. The ice shell thins, cracks more violently, and the ocean might lose its protective lid. Water exposed to the vacuum of space does not last. It boils, freezes, and drifts away as a thin haze of crystals. The same is true for Enceladus, that small bright moon spraying its salty plumes. Its orbit dances with another moon, Dione, and that dance is what keeps it warm. If the rhythm ever shifted, the warmth could fade. Some researchers wonder whether Enceladus has only recently become active, and whether its ocean might be a passing phase rather than a permanent feature. Others argue the opposite, that the moon has held liquid water for most of the solar system's history. The evidence is still being gathered. Around other stars, the picture grows even more uncertain. Astronomers have found thousands of planets beyond our sun. Some are rocky, some are gas giants. A few seem to be water worlds, perhaps wrapped entirely in deep oceans or thick layers of ice, but we cannot yet see beneath their surfaces. We can only guess. One idea is that ocean moons might be common around giant planets in distant systems, wherever a large world holds a family of smaller ones. Tidal heating could keep some of them warm inside. If that is true, the galaxy might contain billions of hidden seas, far more than the number of warm, sunlit planets like Earth. A competing view is more cautious. Tidal heating requires a precise arrangement of orbits, where moons tug on each other in just the right way. Such arrangements may be rare, or may not last. Some researchers suspect that many young moons start with warm interiors, but cool off quickly, freezing solid within a few 100 million years. By that view, long-lived ocean worlds might be unusual rather than common. We do not know which picture is closer to the truth. Even Earth, with its sunlit seas, sits on a knife's edge. Our planet circles the sun at just the right distance for liquid water to pool on the surface. A thin blanket of air traps enough warmth to keep us from freezing, yet not so much that we cook. A magnetic field, generated deep in the molten core, deflects the worst of the solar wind. The moon steadies our spin, keeping the seasons gentle. Each piece fits with the others, and the whole arrangement has held for billions of years. Change any one of these, and the story might have ended differently. Ocean moons offer a different kind of stability. They do not depend on a thin, warm atmosphere. They do not need to sit in a narrow, sunlit zone. Their oceans are tucked away inside, shielded from radiation, shielded from cold, kept warm by the slow grinding of gravity. In some ways, this hidden kind of habitability might be more durable than our own. A star could flare. A neighboring planet could shift. The surface above could freeze harder. And still, deep inside, the dark sea would carry on, or so one theory suggests. Another holds that even sealed oceans are not truly safe. Given enough time, every source of heat fades. Every orbit drifts. Every shell thickens. Perhaps these worlds are simply slower clocks, ticking toward the same eventual silence. For tonight, we do not need to choose. We only need to notice how much had to go right for any ocean, anywhere, to exist at all, and to wonder how many such balances are quietly holding, out there in the dark, around stars we will never visit. Picture, for a moment, an ocean that has never seen the sun. Not once, in all the long ages since it first formed. Above it sits a roof of ice many miles thick, blocking every photon, every hint of sky. Below it, perhaps, lies warm rock, slowly leaking minerals into the dark. And between, only water, cold, salty, still, and silent. This is the setting for one of the deepest open questions in planetary science. Could something be alive down there? Not visiting, not arriving from above, but living, drifting, perhaps even thinking in waters that have never known light. On Earth, life almost always begins with the sun. Plants drink sunlight and turn it into sugar. Animals eat the plants. Even creatures in the deep sea usually depend in some long chain on what grew up in the light far above them. But there are exceptions. Around hydrothermal vents on the ocean floor, whole communities thrive in total darkness. They feed on chemicals leaking from the rock. Tube worms, pale shrimp, ghostly crabs. None of them need the sun at all. They are powered by the planet itself. If life can live this way here, then perhaps it can live this way elsewhere. That is the hopeful thought behind the search for life beneath the ice of Europa, Enceladus, and the other hidden oceans. The recipe seems simple enough. Liquid water, warm rock, a trickle of energy, time. But simple recipes do not always cook the same dish. And this is where the mystery deepens. One view holds that life is, in some sense, easy. Give it the basic ingredients and enough time, and it will find a way to begin. Under this view, the hidden oceans of our solar system might be quietly teeming. Tiny single cells, strange microbial mats, clinging to the underside of the ice. Maybe, in the very oldest and largest oceans, something more complex still. Schools of soft, blind swimmers, drifting in slow currents, listening to the groans of the shell above them. Another view holds the opposite. Life, by this thinking, is rare. The leap from chemistry to biology may require very specific conditions, conditions that almost never line up. Under this view, the hidden oceans might be beautiful and empty. Perfect chemistry, perfect warmth, and not a single living cell anywhere in them. The water just sits there, mixing and circulating, century after century, with no one to notice. We do not know which view is closer to the truth. We have only one example of life beginning, and that example is us. From a sample size of one, you cannot tell whether life is a near certainty or a near miracle, and the question grows stranger when you think about how such life would live. In a permanently dark ocean, there are no seasons, no sunrise, no moonlight, no flowers blooming in spring. Time would be measured only in the slow rhythm of tides pulled by a distant giant planet, or in the cycles of warm water rising and falling from the seabed. A creature there might never know that anything else exists. Its whole universe would be the water around it, the ice above, and the stone below. Some researchers wonder whether such isolation might shape life in unexpected ways. With no light to chase, eyes might never appear. With no surface to crawl onto, limbs might never form. Senses might lean entirely on touch, taste, and the faint pressure of sound. The bodies of these creatures, if they exist, might look nothing like anything we have ever seen. They might be soft, slow, transparent, patient. Others wonder if life in such a closed system would even survive for long. On Earth, ecosystems are constantly fed by sunlight and weather. Beneath an ice shell, the energy supply is much thinner. Perhaps life could begin in such places, but never grow rich or complex. Perhaps it would always remain microbial, a thin film of cells coating the rocks, going about its quiet chemistry for billions of years, and nothing more. There is also a more haunting possibility. Perhaps life arose in some of these oceans long ago, then died out as the warmth faded. Perhaps the fossils of alien microbes sit frozen into the ice right now, waiting for a probe that has not yet been built. We cannot yet tell the difference between a living ocean, a dead ocean, and an empty one. Not from here. The water is sealed away, the ice is thick, and our instruments still sit far above. The question of whether something drifts in that permanent dark remains exactly what it has been for decades, open, unresolved, and quietly, patiently waiting. Every ocean needs a power source. On Earth, the sun does most of the work. Sunlight warms the surface, feeds the plants, and stirs the air that pushes the waves. The whole living world runs on a steady flow of energy from a single bright star. But the oceans beneath the ice get none of that warmth. They live in permanent dark, sealed off from the sky by miles of frozen shell. So the question that hangs over every hidden sea is simple. Where does the energy come from? And will it last? The most likely answer is tidal heating. As a moon swings around its giant parent planet, gravity squeezes it gently from side to side. That squeezing warms the rock and ice deep inside, the way a paperclip grows warm when you bend it back and forth. 4 moons, like Europa and Enceladus. This slow flexing seems to be the main source of warmth that keeps their oceans from freezing solid. But tidal heating depends on the dance between worlds. Moons drift over time. Orbits change shape. The slight tug from a neighboring moon can either deepen the squeezing or smooth it out. In 1 million years, the rhythm may be much the same. In 100 million, it may have shifted in ways we cannot easily predict. Some researchers think Enceladus may be a fairly young ocean, perhaps only a few 100 million years old. Others think it has been warm for far longer. The evidence is incomplete, and the two views still sit side by side. The same uncertainty applies to many of these moons. We can measure their warmth today, but we cannot easily read the story of their warmth across deep time. There is another possible energy source, much quieter and far older, deep inside the rocky cores of these moons. Traces of radioactive elements slowly decay, giving off heat as they break down. This is the same slow warmth that keeps Earth's interior molten. It does not need a giant planet nearby. It does not need tides. It only needs time. That second source matters for worlds like Callisto or Pluto, where tidal heating seems weak or absent. If their oceans exist at all, they may be kept liquid by this quiet radioactive glow, perhaps helped by salts and ammonia that lower the freezing point. One theory holds that even a thin internal sea could last for billions of years this way. Another suggests these oceans may already be slowly freezing from the outside in, thickening their shells year by year. Stretch the clock far enough, and every energy source begins to fade. Radioactive elements decay until very little is left. Tidal dances slow as moons drift to wider, calmer orbits. The squeezing softens, the warmth thins. In the very long future, many of these hidden oceans may simply freeze, locking whatever they once held into solid ice from core to crust. And yet the sun itself is changing too. Our star is slowly growing brighter as it ages. In 1 billion years or so, its light will be strong enough to make Earth's surface too hot for liquid water. The blue oceans we know may boil away into the sky. But farther out, in the cold belt where the icy moons drift, that same brightening Sunday may be a gift. The outer solar system could grow gentler. Surfaces that are now frozen hard as stone may soften. Shells that are now miles thick may grow thinner. For a while, the hidden seas may sit closer to the surface than they ever have before. What this means for any life that might live in those waters is one of the most beautiful open questions in all of science. If something is alive in the dark sea of Europa right now, fed by warm vents on the ocean floor, that life is bound to the slow heartbeat of tidal heating. As long as the squeezing continues, the vents may keep glowing. If the squeezing fades, the vents may cool. We do not know how quickly such a community could adjust, or whether it could survive a long, quiet stretch by sleeping in the rock. There may even be a window far in the future when the warming sun and the thinning ice meet in just the right way. A moon that is sealed today may become a moon with cracks open to the sky. What lives inside, if anything lives inside, might briefly meet starlight for the first time, or it might not. The timing may be wrong. The window may close before anything reaches it. For now, the energy keeps flowing in the dark, slow and patient, and the question of how long it will last drifts gently with the tides. Step back now, as far back as the mind can reach. Picture the whole solar system spread out like a wide, slow wheel of light and shadow. The sun at the center, warm and steady, the rocky inner worlds turning close to its glow. Then, far beyond the warmth, the great cold begins. And in that cold, scattered across the dark like buried lanterns, the ocean worlds hold their secret water. These hidden seas have been there for a very long time. Some of them may have stayed liquid for nearly the full age of the solar system, while continents drifted on Earth, while mountains rose and wore down again, while ice ages came and went. The ocean beneath Europa's shell kept turning in the dark. The plumes of Enceladus kept whispering into space. The deep brine of Ganymede kept pressing against its mantle of high-pressure ice. Quietly, patiently, with no one watching, now look further forward in time. The sun will not shine forever. Several billion years from now, it will swell into a red giant, larger and cooler, flooding the inner system with heat. Earth's oceans, if any remain by then, will most likely boil away. The blue world we know will turn dry and bare. But out among the icy moons, something strange and beautiful may happen. The extra warmth from the dying sun could thin those frozen shells. Worlds that spent billions of years locked beneath ice might, for a brief cosmic moment, open to the sky. Whether anything could survive that change, or even take advantage of it, is one more open question with no clear answer. After that, the sun will shrink to a small white ember, and the cold will return deeper than before. The tidal squeezing from the giant planets will go on, though. As long as Jupiter and Saturn keep their gravitational grip, the inner moons will keep flexing. The heat from that flexing does not depend on sunlight. It comes from gravity itself, from the slow give and take between worlds. So the hidden oceans could outlive the sun's bright years. They could keep their dark waters warm long after the sky above their ice has gone quiet and dim. This is a strange thought to sit with. The places in our solar system most likely to keep liquid water the longest may be the ones that never saw much sunlight to begin with. Life, if it exists in those seas, would not notice the sun's slow death at all. It would feel only the steady warmth of the rocky floor, the gentle drift of mineral-rich currents, the soft pulse of tides driven by a giant planet, wheeling overhead. Pull back further still. Think of our galaxy with its hundreds of billions of stars, and the countless moons that must orbit the giant planets out there. If tidal heating is common, and the early evidence suggests it might be, then hidden oceans could be one of the most ordinary features of the universe. Surface oceans like Earth's may be the rare case. Buried oceans, sealed under ice, warmed from below, lasting for tens of billions of years, may be the rule. Whether any of them hold life is still unknown, but the sheer number of possible homes is humbling. And remember where the water itself came from. Every drop in every hidden sea began as hydrogen forged in the first minutes after the Big Bang, joined to oxygen built inside stars that lived and died long before our sun was born. The salt dissolved in those alien oceans came from supernovae, from the slow burning of giant stars, from the violent end of suns we will never see. The minerals on those dark sea floors were cooked in stellar furnaces and scattered across space. So the ocean under Europa's ice is, in a real sense, made of starlight, cooled, gathered, and tucked away inside a moon. The calcium in your bones has the same story, the iron in your blood, the water in your eyes. You and the hidden oceans share a family history written in the depths of ancient stars. When you wonder about life beneath that distant ice, you are wondering about a cousin made of the same atoms, in a different cradle lit by a different light, or perhaps by no light at all. The mystery does not close tonight. It opens wider. Somewhere, right now, a current is moving slowly through a sea no one has ever seen. A grain of salt is sinking through black water under a sky of ice. The universe is quietly busy with its secrets, and we are only beginning to listen. And so, we come to the quiet edge of the ice. We have wandered far tonight, past moons and dwarf planets, past plumes and fractures and slow magnetic whispers. We have sat with the thought of oceans we have never seen, oceans no human eye may ever look upon, held beneath shells of frozen white. Now the wandering can simply rest. Picture, for a moment, a small moon far from any sun. Its surface is pale and still. Cracks run across it like fine veins drawn in chalk. There is no wind there, no sound, no weather in the way we know weather. Only the long, slow turning of the moon around its giant parent world, and the faint glow of distant stars on the ice. Beneath that ice, the water is dark and quiet. It may be salty, it may be warm at the bottom, where the rocky floor meets the sea. It may be utterly empty. It may be softly alive. We do not know, and tonight we do not need to know. That is the gift of an open question. It asks nothing of us. It does not demand a verdict or a side. It simply waits, the way an ocean waits, patient across billions of years, while small, curious creatures on a blue world build telescopes and send slow machines into the dark to listen. Think of how many such moons there may be. In our own solar system, we have found a small handful with strong hints of hidden water around other stars. There are likely billions of icy worlds, each one a sealed vessel, each one keeping its own quiet answer. Some will be barren. Some may hold strange chemistries that never quite became life. And somewhere, perhaps, a dark sea is stirring with something gentle and slow, something that has never known the sun. We cannot say which is true. The galaxy is wide, and our instruments are young, and the ice is thick. But the question itself is a soft companion. It reminds us that the universe is not finished telling its story. There are still chapters under the crust. There are still pages we have not turned. Imagine that small moon again, turning slowly in the deep above it. The great curved arc of its parent planet hangs in the sky, ringed with pale bands of cloud or thin shining dust around them both. The wider system drifts, planets and asteroids and comets, in their long, slow dance, and around that, the galaxy itself rotates, a wheel of soft light 100,000 light years across, taking 200 million years to complete a single turn. You are held inside all of that. The bed beneath you sits on a small, warm world with its own ocean, open to the sky, full of light. That ocean is connected in a quiet kinship to every hidden sea we have spoken of tonight, the same simple molecule two small atoms and one larger, one gathered into water across the cold, dark reaches of space. The same patient chemistry working everywhere, in different temperatures, under different pressures, beneath different skies. It is a soft thing to know, whatever else is true of the universe. Water is common, and oceans are common, and the conditions for wandering may be common too. We may learn more in our lifetime. A small craft may one day drift down through a plume, or a future probe may melt a slow path through a shell of ice, and listen with careful instruments to whatever sings or does not sing in the dark below. We may find nothing, we may find everything, we may find something in between, something we do not yet have words for. For tonight, let the question stay open. Let the moons keep their secrets a little longer. Let the dark seas rest beneath their ceilings of ice, undisturbed, the way they have rested for billions of years before anyone thought to look. There is no rush. The universe is in no hurry, and neither are you. Let your breathing slow. Let the images soften. The cracked white face of a distant moon, the faint blue glow where ice meets water, the slow turning of a ringed world above a frozen sea, a galaxy wheeling gently in the deep. You are small, and the universe is vast, and that is a kind and quiet truth. You are held by it. You always have been. Sleep now, with the wandering as your blanket, and the hidden oceans as your soft companions in the dark. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.